one big concept called Big O. This is our way of measuring speed and efficiency, how well data structures are actually operating in different scenarios. For example, if I'm in New York and I want to go to California, I could walk there, it might take me a month. I could bike there in a couple weeks, I could drive there in a few days, or I could fly there in just a few hours. Different vehicles are optimized for different scenarios, just like different data structures are also optimized for different scenarios. Now for vehicles, we measure them by miles per hour, but for the speed of data structures and how they operate, we use time complexity or Big O notation. If you're not understanding this, let me break down 4 different types of Big O notation. First one, we got O of 1 constant time. This is the fastest an algorithm can operate. Think like rocket ship, speed of light. O of 1 means the operation takes the same amount of time no matter how much data there is. Imagine you have a grocery list and you want to grab just the first item on the list. Whether that list is 5 items, 500 items, 5,000 items. The operation is the same exact thing. You just need to take the first one instantly. There's no extra effort despite how long the list is. So it's super fast and
Yeah, so these are all things that just follow a basic concept beyond a law of physics. Within the domain of dimension that it looks into, the entire physics of that. There's a compatibility of the system itself that you're gonna go off on somehow around under. Yeah. No, so when you design the time depend on what you use, because as I mentioned physics, because the fact that the system itself is real and it hits up due to energy being dispersed on that system itself as well. Yeah, so the heat is not good when it generates noise inside the system itself. Because the system itself is like physical. So just imagine you have something in there that will accumulate heat, and eventually the chemicals in there, like the glue, start to melt. Everything starts to like fall apart into all compatibilities because of the fact that there's noise happening now. The molecules get to like spread apart even further and create space around the space a lot, and then eventually somewhere in the space within the space, that's like a lot of space in the air inside the space. Yeah, the electrons and the molecules become tougher to travel to another molecule. Yeah, because there's like the spaces are like too far. Yeah, so that's where you stop. Yeah, that's where you start to have like a lot of noise around the space, and then with your resistance become harder. So then you require more energy to go off on like some create a proper system that can still function. So that's what there's operating range. That's why it's like temperature in there. What's up? And then eventually you do like some systems that you want someone calculate that you can run at the speed of your based off like the property of the system that you operate under. Now you use different time inputs for different things on the special. Yeah, for no depend from the programs, but at the same time it does a revolution back inside the signal controls for like mechanical engineering the systems. Because you have to remember that again, the space and the domain that I mentioned. Yeah, you go back and forth in between different fields of like sciences that you use on the space. Because you're gonna find the same thing inside different schools of engineering. It's just that they use it as a basic to be able someone to create a table on the layout or like things that's like geometrical on the space a lot. Yeah, and then because of the fact that it's somewhat geometrical, it becomes sequential and then it becomes more logical on the space. So that's why you start labeling your computer program as if you were designing a mechanical engine or something like a set of gears and wheels on the space.
Fastest an algorithm can operate. Think like rocket ship, speed of light. O of 1 means the operation takes the same amount of time no matter how much data there is. Imagine you have a grocery list and you want to grab just the first item on the list. Whether that list is 5 items, 500 items, 5,000 items. The operation is the same exact thing. You just need to take the first one instantly. There's no extra effort despite how long the list is, so it's super fast and super efficient. A level above that, we have O of n, linear time, where n, in this case, represents the amount of data that we have. This is still a pretty fast operation, so you can imagine not speed of light, but like supercar. And specifically O of n, this is when the amount of data increases, the time it takes grows at that same rate. For example, if you have a list of names and you need to find a specific name, the worst case is you have to check every single name until you find that name. If you have a list of 10 names, you might have to do 10 checks. If there are 1,000 names, you might have to do 1,000 checks. We don't know the position in the list like we did for the O of 1 scenario, and so as the data increases in size, it takes longer because there's just a longer operation, just more to deal with, but it's a very predictable increase. A level above that, we have quadratic time, O of n squared. Think of biking from New York to California. I mean, like very, very slow. And this happens when every single item in a data set needs to interact with every other item. Imagine you have a classroom full of students, and each student has to shake hands with every other student. If there are 10 students, that means 10 times 10, 100 handshakes. If there are 100 students, that is 100 times 100, 10,000 handshakes. The amount of work this operation has to go through grows way too fast the more students that are added into the mix. And if you have an algorithm that takes O of n squared.
Yeah, that's how I mentioned that. Yeah, due to like physics, other things I say to like heat, other things I know what's up. And the beauty about mathematics and the functions itself is that it's just that they make it sound as if like you only have to choose one function depending on what you do specifically. They don't mention that in today's age, the way that you combine these functions over here, yeah, you can combine them for like different purposes, man. Especially, yeah, depend. No, because if you have like a large amount of data, where you mention that so many names on the special, you might want to go off like use a system like that to be able to maintain a magnitude of that system itself, and then you combine it with other systems. Yeah. Well, the way that it's done nowadays, and how it looks, as almost as if it's like this, like yeah, in terms like all beauty, more like coding complexities and stuff. Yeah, versus that simple stuff for them, that's just there. Because originally when you learn, and you go on for you learn to do just the what's it myself, what's it? Yeah, you learn to just do the square, and then you find techniques to go from like wave the square like maybe 1 million times over, and be able to like make it move in like an exotic fabric way. Yeah, in the 2-dimensional field. And then that's your evolution of like the real skill that you've been employing. That's how the mental work. It's just like no, the building blocks is always good to remember for troubleshooting and maintenance, more or less. Because you have to remember you have to simplify your workplace. Or so you use the basic as always to be able to simplify to the simple level, or the techniques of it to be able to like someone be proper in that system.
Time, O of n squared with every other student. If there are 10 students, that means 10 times 10, 100 handshakes. If there are 100 students, that is 100 times 100, 10,000 handshakes. The amount of work this operation has to go through grows way too fast the more students that are added into the mix. And if you have an algorithm that takes O of n squared time complexity, just know that's a really slow, really bad algorithm, and chances are there's a better scenario. Now, the fourth scenario I want to talk about is a slight curveball, and that is O of log n, logarithmic time. And this one is faster than O of n, but slower than O of 1. So it's not the speed of light, it's like the speed of sound. It's still really fast. An example for you to understand this is, imagine we're trying to look up a word in the dictionary. Typically, if you have like a random word, what people generally do is they open up the dictionary to the middle, somewhere in the middle. And from there, you decide, does the word I'm looking for come before or after the current page I'm on? And so depending on that, you'll jump forward or backward. And you'll repeat that process until you find your desired word.
So you have to remember that that you don't just use that to go from like be inside the dictionary or for words and stuff. Yeah, it's just the way that you arrange the system to then go off on like some control how quickly you're gonna go off and have like a reducing latencies. That further. So a good example would be the virtual desktop for like the VR. So because of the fact that it connects to a Wi-Fi system, yeah, it gets delayed and you have a small lag in there. That's gonna be like maybe like 2,000 milliseconds. Yeah, so latency. So you get a lag from the system itself. So yeah, which means that something slow down depend on like how long it takes for a code to run to be able to somewhat hold other codes together and like synchronize them and like keep it in pair. Also not keep it in pair. It's like you have to like someone make sure you ever seen a servo motor? Yeah, where they operate almost in synchrony. But at the same time, the main thing that's going to somewhat limit the synchrony would be the distance in between the two, and then the cable size with the resistance that be somewhat happening to be somewhat delay, or like someone impede the signal that to travel to the wire and the cable itself. So yeah, so some of these systems and like some of the functions that you use with that time system will reduce latency on the space, but no, because you have to find shortcuts on optimization that you then somewhat minimize and then try to multiply and replicate over and over again until you restructurize an entire space for a distance itself. Also to be somewhat optimized surfaces or like the internal makeup material of that system itself. So you rewrite the path and then you optimize the path to create a shorter path, and like it's like you're designing a complex set of like blood vessel to our body. And then you get to like somewhat right when is it that those blood vessels can open up and close on the space.
Each time we're jumping pages, we're cutting the amount of time that we're looking in our search by a half. We're not going through every single page in a dictionary. That would be O of n. Rather, we're going half, and then half of that, and the search space of the operation just gets smaller and smaller. And actually, if you look at a logarithm graph, at a certain point, as you keep increasing the input, the difference in the output is so small and so marginal. And so these are the different time complexities that different data structures can have. And now that we understand how things are getting measured, let's start.
Yeah, no, because I have to go off and like create some transducers and systems. Yeah, no, so I use this technique over there, and that's like it's almost like the gold filters. They used to go off and like somewhat filter out like big boulders for like smaller rubbles. Yeah, no, when they do their little gold things with them, so you filter out the small stone from like the bigger stone of them, like the boulder made out of gold. That you might find inside the California River. Yeah, so no, so when you have different gradients, you want to specify out. The closer you get to like this gradient over here, the least light you get to like penetrate to. What's up? But if you have like a million of these, yeah, it's just like water. Yeah, so just imagine that water will go off and like a filter through each of these systems, and then each of these systems become colder and colder and colder around this place. So yeah, eventually that water will start to like somewhat freeze, and then eventually that density will prevent more water from even flowing through. So that's why you get to like somewhat freeze and stop a quantity. Yeah, you get to like somewhat dilute and slow down and stop and freeze a quantity throughout the system, and then be able to like somewhat let it pass through towards a certain interval within nanoseconds or so on. Yeah, so that allow you to go off and like capture light and be able to like stop it, freeze it, and then retrieve some release it more in the space. So you get to capture movements. Yeah, and like slowly slow down time while the movement is happening and be able to somewhat stop it at one point, just to be able to create an analysis to a computer program and the system itself. So you make the entire quantity easier and like simplified to go off and like somewhat studied by the computer program, how you gonna write the algorithm to go off and like pick up details on the system itself to go off and put it as data and then put it into a function and then another database to then be able to like translate it into like whatever it is that you want to as a quantity itself, because of the fact that you'll be making a mechanical adjustment to it. So you just need to turn this into like a digital system, and then from there on you just turn into mathematics and like logic for what you want to do specifically.